At the end of this video, you should be able to calculate the pressure exerted by a fluid and calculate how pressure varies with depth in a fluid. Pressure is force per unit area. In the examples that we see on the screen, the fluid exerts pressure, for example, if you're swimming, on your eardrums. Pressure is a measure of how much force is applied over a given area. And it can be written as shown on the screen here. P, pressure, is equal to F over A, or force divided by area. The SI unit for pressure is the Pascal, represented by a capital P lowercase a, which is equal to 1 Newton divided by a meter squared. The Pascal is a small unit of pressure. So the pressure of the atmosphere at sea level is about 1.01 times 10 to the 5th pascals. This is also known as 1 atmosphere, or ATM. For the purpose of calculating pressure, 10 to the 5th pascals is about the same as 1 atmosphere. Now, when you pump a bicycle tire, you are demonstrating Pascal's principle, or Pascal's law. Pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid, and therefore also to the walls of the container. For example, you apply a force on the pump that in turn exerts a force on the air inside the tire. The air inside the tire then responds by pushing not only against the pump, but also against the walls of the tire. And as a result, the pressure increases by an equal amount throughout the tire. If we consider a hydraulic lift, like the one on the screen here, we can see that it makes use of Pascal's principle. Applying a small force, which we can represent as F1, to a small piston, which has an area, A sub 1, causes a pressure increase, represented by P sub inc, in the fluid. This increase in pressure is transmitted to a larger piston of area 2, or A2, and the fluid exerts a force F2 on this larger piston. And so we can rearrange this equation to come to a very useful equation. The increase in pressure, again, which is represented by P sub inc, is equal to F2 over A2. Combining the equations gives the following equation. F1 multiplied by A1 is equal to F2 multiplied by A2. But if we multiply both sides of the equation by A2, we can result in a calculation of the F2, which is going to be F2 over A1 multiplied by F1. So the output force, which is F2, is smaller than the input force, F1, by a factor equal to A2 divided by A1. However, the input force must be applied over a longer distance. So using a hydraulic lift does not reduce the work needed to lift the truck.
A small force applied to a piston with a small area causes the pressure in the fluid to increase. According to Pascal's principle, this increase in pressure is transmitted equally to every point of the fluid and to the walls of the container. Pressure is defined as force per unit area. The pressure increase at the small piston is equal to the force over the area of the piston. This pressure is transmitted through the entire hydraulic system. The larger area of the piston supporting the truck feels the same pressure. A little algebra gives the following result, which we can rewrite like so. Pascal's principle that pressure in a fluid is the same everywhere has just allowed us to create a new simple machine. The force output, F2, is just the force input, F1, times the ratio of the areas of the pistons. The output force is now far larger than the input force.
Pressure varies with the depth in a fluid. Water pressure increases with depth because the water at a given depth must support the weight of the water above it. Imagine a small area on the hull of a submarine. Sorry about that. The weight of the entire column of water above that area exerts a force on the area. The column of water has a height represented by h. Now, if the density is the same throughout the water, the pressure at this depth due to the weight of the column of the water, which is called the gauge pressure, can be calculated as follows. Gauge pressure is equal to P is equal to rho times H times G. Now, the total pressure at this depth includes the pressure exerted by the atmosphere at the surface, which is represented by P sub 0, sub naught. The total pressure, also known as the absolute pressure, at a given depth in a fluid of uniform density, which is represented by lowercase p, is as follows. The fluid pressure is a function of depth. So again, absolute pressure is equal to atmospheric pressure plus the product of density, free fall acceleration, and depth.
Consider a fluid in a container. The pressure at the surface of the fluid is caused by the weight of the air above it. This is called the atmospheric pressure. Now consider a certain volume of fluid in a box. The fluid pressure at the bottom of the box is greater than the fluid pressure at the top of the box. This is because the lower layers of the fluid have to support the weight of the fluid above them. The absolute pressure at a given depth, h, in a fluid is the sum of the atmospheric pressure and a second term that is the product of the fluid's density, the free fall acceleration, and the depth. Note that Pascal's principle does not take this into account. Pressure in a container is equal for all points at the same depth, not for all points at any depth.
At this point, you should be able to calculate the pressure exerted by a fluid and calculate how pressure varies with depth within a fluid.